Okay, so in section 4.2, we're going to learn about the numerical method called Euler's method. And Euler's method helps us to approximate the solution of a first order differential equation. So let's define what a differential equation is first. So a differential equation, or an ordinary differential equation, is an equation containing an independent variable, it could be x or t, and a combination of a dependent variable y and derivatives of y. And so in this class, the only thing we're going to work on are first order differential equations, and they contain only the dependent variable y and its derivative y prime. So I'm going to put in the acronym here. This is ODE for ordinary differential equation. It only involves y, the derivatives of y, and its independent variable. And we're going to do only first order in this class, and first order only contain one derivative. Okay, so here's some examples. So the goal is for us to actually find the solution to the differential equation, and it is either going to be y of x or y of t, depending upon what its independent variable is. Independent means you can choose x and t. Dependent means once you choose x, y depends on that. Okay. So here is our first example is y prime is equal to xy plus x squared. So this is one derivative of y. Its independent variable is x in this problem. We have been given some initial information that y at a particular point y naught is x naught is equal to y naught. Okay, here is another differential equation, ordinary differential equation. This one is y prime, and notice it is equal to y times 1 minus y. There is no independent variable that shows up in here, but the fact that this says y of x naught equals y naught lets me know my independent variable is x. Okay, in number 3, again, I have y prime appearing as such equal to t squared plus y squared. So here the independent variable is t. And then there's some information given to you that y at t naught is equal to some value y naught. And this is the first example, actually the only example I'm going to give you of a second order ODE. Notice there are two derivatives, y double prime. It does also contain y prime and y, and there are two conditions. Y at t naught equals y naught and y prime at t naught equals y1. You will see this when you take ODEs, which is Math 351 later. Okay. But the only thing we're going to concentrate on in this section are first order ordinary differential equations. So they are of the form dy dx is equal to some function of xy. So that means if I look at whatever the graph of y is, the slope at any given point is given by a function that we know. So if we go back to this first one here, I get f of x and y is equal to xy plus x squared. So in the first one, that's my function. In the second one, I get f of x and y is actually only a function of y by itself, and it is equal to y times 1 minus y. In the third one, I now have a function of t and y because my independent variable is t. and that is equal to t squared times y squared. Okay, and as I said, we're not going to worry about the last example. I just wanted to show you the difference between a first order and a second order ODE. Okay, so we did notice back here at number 2, it was a little different. We said the independent variable didn't appear. So when f of xy is just only a function of y, we say that the ordinary differential equation is autonomous. Okay, the y stands alone. All righty. So here are some examples, and I want to show to you that these are the solutions of the differential equations. So here is the first one. The first one is dy dx is equal to y, and this I claim is the solution. So I can show you that this is the differential equation, the ODE. I claim this is the solution. Well, how can I prove it? Find y prime. So dy dx, or y prime, is actually equal to a e to the x. So now dy dx is a e to the x, and y is a e to the x. This is a true statement. So therefore, that is the solution to the problem. Okay. This y works in the differential equation. Okay, in number 2, you can see it directly just by using implicit differentiation. So does anybody remember implicit differentiation from Calculus 1? That means we are assuming that y is a function of x. Okay, so if I just differentiate, let's do implicit differentiation on what I claim is the solution. So here is the differential equation. Here is the solution. And if we do implicit differentiation, so when we do that, we have to take the derivative on the left-hand side. Well, we have to do 2y, but we have to take the derivative of what's inside because chain rule, it's a function of x. We get dy dx. And on the right-hand side, we end up with 2/3, and the derivative is 3x squared. And so therefore now I get y dy dx is equal to x squared. And that is the same thing. So yes, again, that is the solution to the differential equation. And for this last one, this one is actually rather easy. I claim here, well, here's the differential equation, and I claim this is the solution to the differential equation that satisfies y of -1 is equal to 2. And it is, y of -1 is equal to 2. Okay, so if I take y prime, I get 2x plus 5. And now I'm going to put it into the differential equation. So I get 2x plus 5 minus 2x equals 5. Again, a true statement. So the solution to a differential equation is the function y of x, and it has to satisfy certain criteria. That means it has to work in the differential equation, and it also has to satisfy an initial condition if one is given. Okay, so what does dy dx actually represent? All right. Well, just like we said before, dy dx always represents the slope of the tangent line. To the curve y of x at the point xy. But it also says that the slope at each point xy is defined by evaluating the function f of x, y at the point xy. Okay. So later on in this chapter, we are going to learn how to actually solve a differential equation. Right now, we're going to learn a numerical technique for solving it before we learn how to solve it analytically. So the numerical technique we're going to learn to solve this differential equation is called Euler's method. Okay, so we're going to solve it using Euler's method. So given the fact that we have the differential equation, dy dx is equal to f of xy. So we have the differential equation, and they give us the initial condition here, y at x naught is equal to y naught. What we're going to do is we're going to start off knowing y at x naught being y naught, and then we're going to move forward and find each subsequent point. So let me give you a picture, and then I will explain my formula. Okay. So we are given that y at some x naught is equal to the value y naught. So that point is on the curve. Then we're going to move a distance of h away to the next point x1. Oh, I really don't want that dot there. I want that to be a tick mark. So then we're going to find y at x1. That will be y1. Then we're going to go the same distance again to x2, and maybe y at x2 is y2. And then we'll go again to x3, and maybe y at x3 is y3. And from this, we'll be able to get an idea of what the solution to our differential equation is in graphical form. So whatever this looks like, this becomes our solution y of x. This is the solution to the differential equation. Okay. All right, so how are we going to do that? Well, here we are going to be given a value of h. And h is this distance between any two. So I can easily see that x naught starts us off. X1 is going to be x naught plus h. X2 is going to take x1 and add h. So here is x2, x3. So we can successively find our values for each of our x's. Now the question is, how do we find the y's? So we're going to use this formula to find the y's. So if we know at the beginning x naught and y naught, we can easily find x1, and then y1 is going to take y0. Notice I'm putting 1 in for n. I'm going to add to that h times f of x naught, y naught. So now I know x1, y1. And then I'm going to find y2 is going to be y1 plus hf of x1, y1, and then we're going to keep going. So why does this work? Okay, well, here's why it works. We're going to go way back again to calculus, and we're going to look at the definition of the derivative. So here's how we end up with Euler's method. Okay, so given a function y of x, we can say its derivative y prime of x, by definition, is the limit as h approaches 0 of y of x plus h minus y of x all over h. Where h, we were letting the limit go to 0. But if h is really, really small, so we can write that as much, much less than 1, or h is small, then the y prime of x is approximately y of x plus h minus y of x all over h. So let's multiply both sides by h, and we get y prime of x times h is approximately y of x plus h minus y of x. So solving for y of x plus h, I get y of x plus h is approximately, move the y of x to the other side, plus h times y prime. But remember our differential equation. In our differential equation, y prime, which is dy dx, is equal to the function f. So I get that y of x plus h is approximately y of x plus h times f of x and y. So in order to get y at the next value, x plus h, I need to know what the values of y are at the previous values. So now a student in one of my other classes says, is there a shortcut to this? No, there is no shortcut to using Euler's method. Most time people write a code in order to solve the problem. So they'll write a code in Python, C, Fortran, MATLAB, whatever their language of choice is, and it can compute it for very, very, very small values of h. What we're going to do is we're going to use some rather larger values of h and at least get some type of an approximation. Okay.
Could you scroll up for a second?
Oh, I can. You want me to go back?
Yes, please.
Okay. To here?
Yes, ma'am.
No problem.
Okay, thank you.
All righty. Okay, let's do this. So I have two major examples. One happens to be autonomous and one is not. So this one says, we're given a differential equation dy dx is equal to y. So we already know that that's going to be an exponential because the exponential is the only function whose derivative is equal to itself. So we know that. And I'm telling you as a starting place that y at 0 is equal to 3. I now need to find y at 1. So I'm going to get an approximation to y at 1. So I've already drawn a chart. So you may want to draw the chart because this is what I'm going to use. For each value of n, I'm going to compute xn and yn. So for x0 and y0, I have 0 and 3. So the first value x0 is 0. The first value of y y0 is 3. I need to approximate y at 1, giving h is equal to 0.2. So I need increments of 0.2 to get me all the way to 1. So it's going to take me 5 iterations to get me up to 1. Okay, so let's get started. All righty. So we know x0 is equal to 0 and y0 is equal to 3. So that's where we're starting. Okay, we need our formula. We don't see it above, so I'm going to write it because we need it. That is xn is yn minus 1 plus h times f of xn minus 1 yn minus 1. All right, so for this one, that says yn is yn minus 1 plus h and f of x and yn. Okay, we can see right here that f of xy is just y. So f of xy is just y. So I get y n minus 1. So f of xy is just y. Okay. X lower 1, x1 is equal to 0.2. Y1, well, we know that's going to be y0 plus h times y0. All righty. So y0 is 3 plus h is 0.2 times 3. So that gives me 3.6. So y1 is 3.6. y2 is going to be y1 plus h times y1. So y1 is 3.6 plus 0.2 times 3.6. And that comes out to be 4.32. Okay. Oh, I forgot to put in x2. How did that happen? X2 is equal to 0.4. Okay. Really? I don't know why it's doing that. I have no idea what it's doing. Okay, much better. All right. X3 is equal to 0.6. Y3, anybody want to give me Y3? We know it's Y2 plus HY2. So what is Y3? Hello?
Plus HY1.
Okay, at this point, I just need to use Y2 plus H. So I don't need HY1. That was used in finding Y2.
I meant 4.32 and
Okay, 4.32 plus H is H is 0.2 times 4.32. So we get 5.184. Okay. X4 is equal to 0.8. So Y4 is Y3 plus H times Y3. So Y3 is 5.184 plus 0.2 times 5.184. And that is 6.2208. Okay. And then the last one, X5, which is finally 1. And then Y5 is going to be Y4 plus h times y4. And that's 6.2208 plus h 0.2 times 6.2208. And that is 7.465. Okay, so I can now say that y of 1 is approximately 7.465. So this is the computed value. Now the solution to the differential equation to dy dx is equal to y, where y at 0 is equal to 3. The solution is y of x is equal to 3e to the x. So the true value is 3 times e to the 1, and 3 times e to the 1 is 8.1548. Okay, so now we can compute the error. So the error is the absolute value of y true minus y approximate. So that's the absolute value of y true, which is 8.1548 minus y approximate, which is 7.465. And that is 0.6898. How do you find the relative error? We found relative error before. How do you find relative error? Given this information, how do I find the relative error? It's a percentage of the error. So how do I find it?
Isn't it the same thing times 100?
Okay, well, we first have to divide by the true value. So it's going to be y true minus y approximate divided by y true times 100. So that's going to be 0.6898 divided by 8.1548 times 100. So that's equal to approximately 8.46%. So that's not terrible. Okay, it's not. So what we end up having here is now we get 0.3, 0.2, 3.6, 0.4, 4.32, 0.6, 5.184, 0.8, 6.2208, and 1.0, 8.1548. So if we were to plot this, so this is 1, 2, 3, 4, 5, 6, 7, 8. So at 0, we were at 3. At 0.1, 0.2, we're at 3.6. At 0.4, we're at 4.32. Then at 0.6, we're at 5.18. And at 0.8, we are at 6.2 here. And then at 1, we're at, oh, that's wrong. This is not the value we got. That's the true answer. The value we got was 7.456. So 7.456 is somewhere around here. And the true value, which is 8.1 something, is up here. So this is our error right there. And as you can see, this is actually an exponential curve. It does not look exponential because I stretched it out so that we could get the values, but it actually is growing rather quickly. It's growing rather quickly. Okay, any questions about that? Okay, I have one more example. Okay. Here's the next example. Here's the differential equation. dy dx is 2xy. Here's the initial value. Y at 0 is 2. And we're trying to find y at 2.4, an estimate, and they tell you what h is. Now, I can say this, the smaller h is, the more iterates you have to do, but the better your approximation and the smaller your error. Okay, so we're going to, here's the table. Okay, we're going by 0.4. So we have 0, 0.4, 0.8, 1.2, 1.6, 2.0, 2.4. So all of these are our x's that we're going to evaluate. N tells us which step we're at. So this happens to be x0, y0 is 0, 2, which is what we got from our initial condition. And then we now need to find each successive iterate until we get to an approximation for y of 2.4. Okay, so let's get started. So the first thing we need to see, again, is that yn is equal to y at n minus 1 plus h times f of xn minus 1, yn minus 1. So what f in this problem? F of xy is what? What is f of xy?
2. No. Wait, no. I don't know.
Yes, you do. Rodney, here it is. Remember the original form, dy dx was equal to f of xy?
Yeah.
Okay, so now come back and tell me what's f of xy in this problem.
Or the derivative 2 is 0.
Okay, we're not taking the derivative. We're just saying dy dx is equal to f of xy. So what does f of xy have to be?
2x, y.
2xy, good. All right, so now I'm going to put that in. So I get yn is yn minus 1 plus h times 2 times xn minus 1 times yn minus 1. So my formula now is yn is yn minus 1 plus 2 times h times xn minus 1 times yn minus 1. Okay, so that's the formula we're going to use. All right, here we go. We're going to start off with x naught is 0, y naught is 2. Now, does x naught always have to be 0? Absolutely not. It can be something else. All right, I just happened to, for both of these problems, x naught was 0. It could be anything that they want to start the problem out as. Okay, so now x1, well, that's 0.4. I can see that from my chart. So now y1 is going to be y0 plus 2 times h times x0 times y0. Okay, so all I've done is put in n equals 1. Okay, so y0 is 2. Plus 2 times h, which is 0.4, times x0, oh, well, that's 0, times y0. Y0 was 2. Okay, it forgot this 2. I don't know why it forgot the 2 here. Okay, there we go. Now it sees the 2. Okay, so this is just 2. Okay, x2 is 0.8. y2 is y1 plus 2 times h times x1 times y1. So that's 2 plus 2 times h, which is 0.4, times x1, which is 0.4, times y1, which is 2. So that's 2.64. Okay. X3 equals 1.2. Y3. Anybody want to be able to tell me what Y3 is? With the formula and then plugging in the numbers. What's Y3? Hello? This is Y2 plus 2 times H times X lower 2 times Y lower 2. $2.64 plus 2 times H 0.4 times X1, I'm sorry, X2 0.8 times Y2 2.64. So that is 4.3296. X4 is equal to 1.6. Y4 is going to equal Y3 plus 2 times H times X3 times Y3. That's going to equal 4.3296. Uh-oh. Plus 2 times 0.4 times 1.2 times 4.3296. And let me check to make sure that is the right number. 8.486, that's right. So I'm going to leave it to you to check to see that you get 19.3491 and you get 50.3051. So therefore, the answer to your problem would be Y at 2.4 is approximately 50.3051. And so on the homework, you will put in whatever decimal accuracy that they want, okay, when you do these problems. All right, and so that is how you do Euler's method. On Thursday, we will actually solve differential equations.